We can use molecular shape to predict how polar a molecule is. Overall molecular polarity depends on both the shape and the bond polarity. It's really important that you understand that in order to figure out if a molecule is polar or not, we need to be able to determine its shape. The polarity of a molecule is usually measured by its dipole moment, which is given in units of debye. But in this class, we're going to mainly be thinking about it qualitatively. And a molecule is polar if it contains one or more polar bonds and if the individual bond dipoles do not cancel. Alright, so an example is carbon dioxide. To determine if a bond is polar or not, you look at the difference in electronegativity between the two atoms that form a bond. So in this case, we're talking about carbon dioxide. The electronegativity of carbon is 2.5. The electronegativity of oxygen is 3.5. So because there's a big difference in electronegativity between these two atoms, each carbon-oxygen bond is polar. However, because carbon dioxide is linear, the bond angle is 180 degrees and the individual bond polarities cancel. So the molecule has no net dipole moment. Two molecules can have the same shape and have different polarities. So this is an example of carbon tetrachloride, chloroform, and in carbon tetrachloride, because this is a completely symmetric molecule, again, even though the bonds are polar, the overall dipole moment is 0 because the bond polarities cancel. You can think about these dipole moments like vectors. So essentially you're adding all of the vectors together, and if the sum is 0, then there'll be no dipole moment. Whereas chloroform, your bond polarities do not cancel. You're going to have an overall dipole moment pointing down. Okay, so let's do an example. Is ammonia or NH3 polar or nonpolar? So this is what the molecular shape for ammonia looks like. This is a tetrahedral electron arrangement or a trigonal pyramidal shape, and the bond polarities look like this. So nitrogen is more electronegative than hydrogen. So overall we have a dipole moment pointing up. So ammonia is polar overall. Now that we've talked about shape, we need to talk about the importance of molecular polarity. So overall molecular polarity depends on the shape and the bond polarity. So you might be wondering, why do we care about the polarity of the molecule? Well, the polarity of a molecule affects the molecule's macroscopic properties. So what we mean by that is it's not just that we have this dipole moment on this really small scale, it's also that polarity is the driving force behind biological reactions, such as protein folding, and other macroscopic properties. And part of this is because if you have a polar molecule and you apply an electric field, the polar molecule will align in the electric field so that the partially positive part of the molecule is near the more negative part of the electric field, and the partially negative portion of the molecule aligns with the positive of the electric field. But it's just important that polar molecules align in the presence of an electrical field. This is important because usually we don't have a molecule in a vacuum. There's other molecules are interacting with one another. And so we can have these really important intermolecular forces called dipole-dipole moments, where the dipoles of two adjacent molecules will align so that the partially negative portion of the molecule is aligned with the other molecule's partially positive portion of the molecule. And an example of this is hydrogen bonding in water. The hydrogens align with the oxygen atoms, so this is the more partially positive, this is the more partially negative, and they form this network in solution. And this is one of the biggest reasons why water has such a high boiling point, because to boil water, you need to disrupt these intermolecular interactions to increase the vapor pressure, and these intermolecular interactions are difficult to disrupt because of these strong dipole-dipole interactions. Another example of when polarity is important is the base pairs in DNA. They also have these dipole-dipole interactions or hydrogen bonding interactions, and this is what holds together the base pairs in DNA. So overall, molecular polarity is very important.